Let us now talk about the conformations of ethane. Structure of ethane should be well known to us. And if we look at this in 3 dimensions and analyze the details a little bit more, we should find out what the bond lengths are and what the bond angles are. So a CH bond in ethane has a length of 1.10 angstroms, so very close to the one in ethane, while the CC bond is much longer, it's 1.54 angstroms. The angle between a C and CH bonds and CC bond is roughly the same as in methane, 109.6 degrees. Now you probably remember that the central sigma bond in ethane is formed by overlap of 2 sp3 bonds, of 2 sp3 orbitals on individual carbons. So this is a sigma bond. Rotation around this bond is free, and you should remember that as well. And so we can talk about at least 2 conformers of ethane. This one, which is what we call staggered, and the alternative, which we call eclipsed. Now, these different rotamers, and these could be called conformers or rotamers. So these rotamers can be represented in another way, which is actually often used in these conformational representations. So if we look at this structure, imagine that we're looking from here down along the CC bond axis. What we'll see is the first carbon in front of us, and we'll see 3 hydrogens in this arrangement. But in the back, we will see that this back hydrogen is in between the 2 hydrogens on the front. And so we're going to show these hydrogen atoms on the back by not going all the way to the center of the circle, but just to the periphery, and this will be the structure of ethane. These formulas are called the Newman projection formulas, and they're very frequently used for representing conformational details. Now, if we want to represent the eclipsed conformation using a Newman projection formula, we can do that as well. Again, looking at it from this side, we'll look at the front carbon and we'll see this hydrogen above and the one on the left and right and bottom. But behind, each hydrogen will be, as the name says, eclipsed by the hydrogen in front. And so what we do then is do just a little slightly offset thing so that we can show them both without overlap, but clearly much closer than they are in this case. This angle is an important one, and here this angle is 60 degrees, while here the same angle is 0 degrees. When we talk about that angle, we refer to it as the dihedral angle, using the Greek letter theta, and this varies between 0 and 60 degrees, with 0 being the eclipsed and 60 being the staggered conformation. The things in between the staggered and eclipsed conformation are called the skewed conformations, and they're intermediately positioned. If we're going to look at this dihedral angle, And it's really important for us to realize that the dihedral angle, theta, is defined by 4 atoms. So in this case, it's defined by the HCCH subunit. And that's an important thing to remember, right? So that's all fine, and ethane tumbles and turns around all the time. But the question is now, well, are all of these conformations completely randomly distributed? Are they all equally favorable? And the answer is no. And that's an important point, that not all conformations are equally favorable. In general, eclipsed conformations are higher in energy. We'll come back to that later. Now, when we talk about these energies of conformations, we need to think what is the parameter that makes one conformation more stable than the other, and what is the thing that changes with the change in the dihedral. And the answer to this question is that the thing that changes is the distance between the CH bonds. And each CH bond has 2 electrons in it, so each bond is center of electron density. And 2 CH bonds repel each other. And so the furthest they are, even if they're not in the same carbon, the furthest they are, the more stable they are. In other words, and this is just rephrasing what I told you already, this is better than this. Now if we're going to display this quantitatively, we're going to use a graph whereas the y-axis will have the relative energy in kcals per mole, and as an x-axis we will have the theta in degrees. If we start at 0 degrees, then that is an eclipse conformation, that is relatively high energy. As we keep increasing the angle, this energy lowers until we reach the value of 60 degrees, which is the stacked conformation, which is most stable. Then we're moving on to the next eclipse conformation, which is at 120 degrees, which is unstable as well. Then we're going to 180 degrees, which is stable, 240, unstable, 300, stable, and 360 takes us back full circle to the unstable eclipse conformation. In this simple case, this sine curve has an amplitude which is equal to 3.0 kilocalories per mole. And that tells us what is the repulsion of eclipsing hydrogens. It's basically 1 kcal per pair of hydrogen. This energy is called the torsional energy. And the barrier to going from one valley to the other is called torsional strain. Two concepts of torsional energy and torsional strain are very, very much related. Let's see now how this thing applies to propane. Well, in propane, we have 2 CC bonds, but the thing about them is they're symmetric. So if you look at the rotation around either one of them, we're going to have 2 conformations. One will be the staggered one. We'll have H, 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 CH3, while the other one will be eclipsed. It will be H, 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 CH3. Now, the graph will have the same shape as the one for ethane. However, the difference in energy between the eclipsed and stagnant conformation should be different, because while before we had the HH repulsion, now we have the CH3H repulsion, and one would expect that CH3 is a larger group, so it's things getting more crowded there than with a single hydrogen. Turns out that that is indeed the case, and that this interaction is slightly more unfavorable, but not by much. And so the graph for propane looks the same, but this difference is a mere 3.3 kcals per mole. In other words, the difference between methyl group and hydrogen repelling another hydrogen with a dihedral angle of 0 is just 0.3 kcals per mole. Now, in the next topic, we will see what happens when we move to even higher system, butane, where now we have two methyl groups that can potentially repel each other, and we'll see how much of a difference that makes.